we worked on this situation before. We found that if we have a positive charge here and a negative charge here, the potential difference between A and B is minus E times D, where E is the electrical field in between. And we found if since the electrical field is given by sigma over epsilon 0, this makes the electrical potential minus sigma D over epsilon 0. Now, remember what capacitance is. Capacitance is charge over voltage. C is equal to Q over delta V. Now, if we replace delta V by its value there, sigma D over epsilon 0, we get this. Now, sigma, surface charge density, it is Q over the area. So if we replace it here by Q over the area, and we have epsilon 0 all the way at the bottom here, so it can come up here, and then the Q's cancel, and we end up having epsilon 0 A over D. So the capacitance for a parallel plate capacitor like that one, it depends only on the area and the distance separating the plates. Epsilon 0 A over D. Very simple expression. It does not depend on the voltage. It depends only on the geometry of the capacitor A and D. Now, if we place an insulator in that capacitor, what's going to happen, the insulator, what we call a dielectric. So when we have a buildup of positive charge in this conductor and negative charge in this conductor, in the insulator, that's going to reorient the molecules so that this side of the insulator is going to have negative charges and this side of the insulator is going to have positive charges. So effectively, it's like we are reducing D. This amount of charge here is going to balance the plus Q here. And this amount of charge here is going to balance the minus Q here. So effectively, my distance is this much and this much. In other words, by reducing the distance, since the distance is in the denominator, we have a larger capacitance. More specifically, the way we get it is through what we call dielectric constant of the insulator, this kappa. Kappa is larger than 1, so the capacitance with the dielectric, with the insulator, is going to be kappa times the capacitance without 1. Or in general, the capacitance then can be written kappa epsilon 0 A over D. Now, capacitors are used to store energy. So let's discuss that for a little bit. Let's assume at one point I have a charge Q here and minus Q here in the capacitor. So the work needed to transfer one charge from here to here, from one plate to another, is going to be equal to Q delta V, which is, remember, delta V related to the capacitance through this equation. So delta V is going to be equal Q over C. And that's what we have here, Q over C, dQ. So the amount of work needed to move the full charge Q of the capacitor from one plate to another is going to be given by this, by adding up all these tiny charges. When we add them up, we end up having the 1 over C comes out here, and then Q dQ, that's Q squared over 2, doing the integration, that gives us this as the work needed. So in absolute value, what that tells us, the energy stored in a capacitor is Q squared over 2C. So the energy is going to be the amount of charge squared over 2C. And rearranging that, write in C. Remember this equation again, write C as Q over delta V. That gives us this expression. Or this expression. Either way you'd like to write it. All of them are telling us the same thing. And that's essentially the main use of a capacitor. In summary, these are all the equations that we had for capacitor. This is capacitance, parallel plate capacitor with no insulator in between. The unit is the farad. That's our epsilon zero. If we have a dielectric, that's what we get. And the amount of energy stored in the capacitor is given by that.